Hello, 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 everybody, and welcome back. Root Beer here, and we are starting Part C on our Canadian Open Mathematics Challenge from 2018. So we'll be starting off with C1. These are the last four questions on the paper. They are each worth 10 marks and each require a nice written solution with full justification. Show all your work, show all your calculations, explain yourself, that sort of a thing. What do we got? Oh, we got three parts here. At Math E to the E Mart, that's cute, Mathy Mart. Cans of cat food are arranged in a pentagonal pyramid of 15 layers high, with one can in the top layer, 5 cans in the next layer, 12 cans in the third layer, 22 in the fourth, etc., so that the kth layer is a pentagon with K cans on each side. And it looks like it's a filled-in pentagon here. We've got a top view, top-down view, and a front view just to sort of help us visualize what exactly they're going on. So, for example, this top can has to be supported by a can below it, because I'm seeing 1, 2, 3, 4. There's got to be another one back there, 5. And then each of these 5 cans in this layer have to be supported by one, and then I'm seeing some extra ones out front, 7 more. 5 plus 7 is the 12 they're talking about. I seem to recall when this came out, a couple of my friends were complaining this wasn't exactly a clear diagram and clear picture. I'm not having trouble with it now, but you might have, and if so, if you'd care to explain the difficulty you were having in visualizing it, that can really help us when we make contests. I mean, I don't make the Open, but I do try and help make other contests, and just knowing how students think and perceive these things is always a great help to us. Anyway, okay, so basically each layer is a pentagonal number. If you're not familiar with pentagonal numbers, you might be more familiar with triangular numbers, where each layer adds one more than the layer before it. Pentagonal numbers work a little differently, but you can see I'm making a triangle here, or you're probably definitely familiar with square numbers. It's where squares come from. Perfect squares, I mean. Okay? It's the same sort of idea, just arrange them in a pentagon. You can have any sort of regular n-gonal number. There are hexagonal numbers, heptagonal numbers, those sorts of things. There's some really cool results out there. So, for example, square is a regular four-sided shape. Every number, every positive integer can be represented by at least, or at most, a sum of 4. You need at most 4 squares to add up to any number. And three-sided figure over here, there's a nice result that says you can represent any number as a sum of 3 or less triangular numbers. Similarly with pentagonal numbers. It's a really cool result. I highly doubt that that's what they're going to be getting at, but it's fun to learn about these things. So, if you're interested, pentagonal numbers. Now, I know pentagonal numbers have a formula. I don't know what it is off the top of my head, like I know the formula for squares and for triangular numbers. But, if I need to, maybe I'll discover it. All right, A part. How many cans are in the bottom, the 15th layer of this pyramid? Okay. So we have some numbers to work with, but there's not the most obvious pattern. I think if we focus on this picture here, because every layer, as I say, contains the layer above it, and then adds on, it looks like 3 more sides. 3 more sides, each with that layer number cans, and then there's these 2 sort of overlap cans that are included twice. So if we were to say, I'm going to use P for pentagon. Let's say let Pn equal the number of cans in the nth layer. We see Pn is Pn minus 1 cans to support the previous layer, let's say. Plus 3, I don't know what to call them, lines or rows of n cans. I can draw a little picture here. Let's draw a little better picture. My angles aren't working out quite right. One angle's too steep. There's n of them here. N of them here, n of them here, and I'll use like a little highlighter or just a different color. These cans are counted twice. So -2 of those cans. Okay, so this allows me to say that Pn is the previous Pn minus 1 plus 3n minus 2. So that gives me a nice recurrence relation. But can I actually get sort of a formula from that? Well, I suppose we could work backwards. And say, oh, well, now Pn minus 1 is 3n minus 1 minus 2 plus Pn minus 2. And then we could work backwards from there. Actually, I can I can drop some of these brackets, make my life a little easier. 3n minus 2 plus 3n minus 1 minus 2, and then we could have 3n minus 2. So this one splits up into 3n minus 2 minus 2 plus the previous one. So we can just keep going down. We'll get 3n minus 2, 3n minus 1 minus 2, plus 3n minus 2 minus 2, all the way down to, let's say, P2, and then we just want to be careful as we split this next one up. Get everything here again, and then P2 splits into 3 times 2 minus 2 plus P1, which we know is 1. But as a fun little fact, we know P1, actually, let's say, P1 can now be written as, it's 1, but that's the same as 3 times 1 minus 2, so that's kind of cool. So now if we group all these together, I'm going to say it's 3, and then I've got an n minus 1, all the way down to a 2 and a 1. And then how many minus 2s have I got? 1, 2, 3. Well, there's 1 for the n, 1 for the n minus 1, all the way down to 1 for the 2 and 1 for the 1. So I can easily count there's going to be there's going to be n minus 2s. So we get a nice little formula. And there's also a formula for this. It's n times n plus 1 over 2, that triangular number formula I was talking about. It's a very handy formula to know. It's always a good idea to know the sum of the first n natural numbers. Sometimes it's also good to know the sum of the first n squares, sum of the first n cubes. I wouldn't recommend you know the sum of the first n fourth powers. I could see it maybe coming up on a really difficult sort of national level contest or even an international contest, but no, most people stop with the squares. So we'll put the question on hold for a moment. The sum of the natural numbers, in case you haven't seen it before, is n times n plus 1 over 2. The sum of the squares, so 2 squared, 3 squared, all the way up to n squared, is n times n plus 1 times 2n plus 1 over 6. This one takes a little while to get used to. Write it out a few times until you have it memorized. A great check for this is to check the first couple, because you can figure out the sum of the first one squares is 1, and if you plug 1 in here, you'll get 1 times 2 times 3, divide that by 6, you'll get 1. And then the next one should be 5. 2 times 3 times 5 divided by 6 should be 5 as well. It's usually a quick check to see that you've got the right sum. And then the last one, the sum of cubes, is the last one I recommend people know off the top of their head. And the only reason I recommend this, it's just so easy to remember. It's just the square of the first one, and there's cool geometric reasons as to why that is. I'm not going to go into that. I'm going to get back to the question. But these are good to know for a contest. Anyway, so the first one allowed me to simplify this bit into this, and now I could probably combine it into a single expression. We don't need it as a single expression for A, but there's a B and a C part, so I feel like maybe we should have them handy. So let's say 3n. I can expand that out and say 3n squared plus 3n over 2. Then minus, we'll say 4n over 2, just to get a common denominator. And so 3n squared minus n over 2. So I'm saying this is my formula for Pn. Now, it's a good idea to check, is this correct? You know, P1, I mean, they give us a whole list of ones that we can check. So, for example, is P3 really 12, according to my formula? Well, that would be 3 times 3 squared minus 3 over 2. That'd be 27 minus 3 over 2. It's 24 over 2. Yeah, that's 12. You can do another one really quickly. 3 times 4 squared minus 4 over 2. That'll be 44 on top over 2. And yeah, that's 22. So this is really working. It's a good formula. What do they want? They want P15. That's all we were asked for. So 15 squared minus 15 all over 2. 15 squared is 225. So we'll get 675 minus 15 all over 2. That'll be 660 all over 2. And that'll be 330. So there's our answer for A. We've shown our work. We showed where this formula came from. Okay. And then we just plugged in and got our answer. But now this is useful. Now if they ever ask me about any other layers, I've got a formula handy. Okay. Speaking of asking about other layers, what have we got for B? Actually, this is catching my eye. It looks like C, they're dealing with triangular numbers. That's kind of cool. Maybe. I don't know. Actually, I haven't read that part. Let's read B part here. The pentagonal pyramid is rearranged into a prism consisting of 15 identical layers. How many cans are on the bottom layer of the prism? So take all these cans. I don't know how many cans there are, but then we arrange it into a prism. So it's some number of cans, and then on top of that is the same number of cans. And then on top of that is the same number of cans. It just keeps going up and up and up and up. Because that's what would make it a prism. Okay, and we know how many layers the prism it'll be 15, so I guess we want to know how many cans are on the bottom layer. Well, we just need the number of cans total divided by 15, right? Divided by 15 layers. If you wanted to, you could explain it's a prism, so there's the same number of cans per layer. I think it's clear. You're more than welcome to add things to it if you want to. So we have to figure out the number of cans. Well, I know how many cans are in each layer. Well, sort of. There's P1 in the first layer, P2, P3, all the way up to P15. Right, so, well, we've got a formula for this. So 3 times 1 squared minus 1 all over 2. 3 times 2 squared minus 2 all over 2. 3 times 3 squared minus 3 all over 2, all the way up to 3 times 15 squared minus 15 all over 2. Well, I can definitely take out a factor of over 2. And I'm going to split it into two sums. First, 3, and I'm noticing I'm getting 1 squared plus 2 squared plus 3 squared all the way up to 15 squared. So it looks like I'll use one of the other formulas I told you about. And then it's minus 1, minus 2, minus 3, all the way up to minus 15. So we've got a formula for those. So we'll have 1/2 3 n times n plus 1 times 2n plus 1 all over 6 minus n times n plus 1 all over 2. Oh, sorry, it should be 15s here. I'm being a bit too general. I'm actually showing how to do it for the sum of the first n pentagonal numbers, which we're not being asked for. Okay, so what can we do here? 1/2. The 3 and the 6 will cancel out, so we'll actually get a 1/2 in here. I'm going to take out a further 1/2, so we'll say 1/4. 15 times 15 plus 1 is 16 times 31 minus 15 times 16. Take out a 15 times 16. We'll get 31 minus 1. So 16 divided by 4 is 4, so we'll get 15 times 4. The reason I'm not combining this into 60 is because I'm about to divide it by 15 layers anyway. And then 31 minus 1 is 30. So we'll say 15 times 120. So number of cans in the bottom layer is 15 times 120 divided by 15, which is 120. There we go. So that was actually a little shorter. It would have been quite a pain if I didn't know the formula for the sum of squares, which goes to show you should know that formula. Especially if you're trying C-part questions on a Canadian Open. These are very good formulas. I wonder if the next question will have to add up sums of these stacks and we'll have to use the sum of cubes formula. Who knows? We will in just a moment as we read the question. Hopefully you already know, because hopefully you tried this question before watching the video. Anyway, C. A triangular prism consists of identical layers, each of which has the shape of a triangle. Number of cans in a triangular layer is one of the triangular numbers, so they're sort of assuming we know what a triangular number is. I mean, I do, but not everyone does. But, okay. So 1, 3, 6, 10, those sorts of things. For example, a prism could be composed of the following layers. They're explaining triangular numbers. Good, good, good. Prove that a pentagonal pyramid of cans with any number of layers L can be rearranged without any extras or without missing a can into a triangular prism of cans with the same number of layers. Did they sneakily make us do that in B? Is 120 the 15th? 120 the 15th triangular number or something? 15 times 8, yeah, it is. It is. Cool. All right, so I have a pretty good strategy for how to do this. So we just want to show that we get the same number of layers. And that is what they made us do in B. We had 15 layers, and we rearranged them into a triangular prism. Well, actually, we didn't they didn't say it was a triangular prism. They just said it was a prism. But I can turn it into a triangle because 120 is the 15th triangular number. It didn't have to necessarily be the 15th triangular number, but 120 is about that range. And I thought, well, that'd kind of be nice. All right, number of layers is L. So we wish to show number of bottom cans equals some triangular number. I'm not going to say for certain it has to be the Lth triangular number. I can't guarantee that right now, although it is kind of interesting that it was the 15th triangular number, the first one I guessed. Anyway, okay, so the total number of cans is P1 plus P2 plus PL. And now we're basically doing what we did a moment ago. 3 times 1 squared minus 1 all over 2. 3 times 2 squared minus 2 all over 2. All the way up to 3 times L squared minus 2, or minus L over 2. And now we can say it's 1/2, 3, 1 squared. I know I just did this and I wrote this out, but I want to be very clear to whoever's marking. And then we'll also get minus 1 plus 2 plus L. So the total number of cans is 1/2, 3 L times L plus 1 times 2L plus 1 all over 6 minus L times L plus 1 all over 2. So those cancel out to a 2. I can take out the halves everywhere. I'll get L times L plus 1 times 2L plus 1 minus L times L plus 1. And so this is, I can take out an L times L plus 1 divided by 4. That's very nearly a triangular number. That's very nearly the Lth triangular number. And we've got 2L plus 1 minus a 1 left over in here. So that's L times L plus 1 all over 2, and then we'll have a 2L here, and I can bring the remaining 2 from the 4 in here. And that gets me an L. L times L plus 1, 2. So with the bottom layer being the Lth triangular number, we get L layers in our prism as desired. There we go. Very nice. So that does it for C1. An interesting start to C part. I wonder what we got in store for C2. We'll have to find out in the next video. Hopefully you'll join me for that. Until then, take care and have a wonderful day.